Thank you, Carlo. Very often the question is asked whether nuclear power is sustainable. I think it's not the right question. The right question is, under which condition will nuclear power be sustainable? That will be somehow the topic of my talk, starting with what is the present status of nuclear power. And then, as you know, in the media, they talk about the renaissance of nuclear power. But the renaissance may not happen. There are a number of prerequisites to it, and I will try to spell them out. First, let's start with what is the past in terms of energy consumption. This is another way of putting the same figures as Mr. Houssin. As you know, in the year 2007, more than 80% of the world energy consumption was just burning fossil fuel. Then you had something like 13% coming from renewables, but most of them coming from biomass. And biomass is very nice when it's during the weekend in your cottage when you make a nice fire in your fireplace. But when it is your only source of energy, means that you have to spend 12, 13 hours just gathering fuel wood and then cooking, and it leaves you very little time to raise your children. So there are two aspects of biomass. If you have only it, not too good. And then hydro, and you see that all the renewables, which are the new renewables, presently are only less than 1% of the world total, but of course, it's growing very fast. Now, nuclear power, you've seen, was less than 6% of the world total energy consumption. It is, in fact, produced in 30 countries, plus Taiwan, and those are the first top 10 producers: United States, France, Japan, Russia. You see that South Korea has now overtaken Germany. Then you come to Canada, Ukraine. China has been in the top 10 for only 2 years, but it's growing fast. And you see that all the 436 nuclear power plants in the world have produced 2,600 billion kilowatt hours. There are presently roughly 12 or more countries where nuclear power accounts for more than 1/3 of the total electricity production. Because I told you about the percentage of energy produced by nuclear power, but nuclear power today produces only electricity. I say today. I will elaborate a little later on. In terms of electricity, it's between 14 and 15% of the world, but as you can see, in a number of countries, it's already quite above 30%. So to put it in a very summary, nuclear power is only 55 years old. Of course, the first nuclear reactor went critical in 1942, but the first plant actually connected to the grid and producing power dates back only from June 54. So in 55 years, we came from 0 to 15% of the world electricity somehow. But as you can see, it's almost as much as hydropower, not quite as much, but close. And if there was no nuclear power, if we were still burning oil to produce power as we were in the early 70s, for instance, then we would have to produce an additional 650 million tons of oil every year, which is bigger than Saudi Arabia production, which is the biggest. So nuclear is very far from being equivalent to oil, but it's at least equivalent to Saudi Arabia, so it's not yet completely negligible. On the bottom part of the picture, you can see that after a period of fast growth in the 70s and early 80s, nuclear has experienced 2 decades of very slow growth, and in fact, a growth mostly located in Asia. But this is the past. Now let's see what's waiting for us in the wings. Well, I was just going to say the general context, but it has been described much better than me, so I will skip this one. Just to say that there is this old fear of oil peak. Now people are thinking it will not be a sharp peak, but kind of extended plateau. But at the end, it will start to decrease. Of course, it's not renewable. And even in a plateau, the oil prices are bound to be rather high. This was just to explain much better before, so I'll skip this one. But in terms of security of supply, the problem of oil is not in terms of reserves, it is more in terms of location. Mr. Houssin has expressed the growing share which is going to come from OPEC. We can say that in terms of conventional resources, I mean the oil that flows, not the bitumen, or in terms of conventional gas resources, 70% of the oil and 40% of the gas reserves are located in a very small region of the world, this kind of small ellipse, which ranges from the south of the Arabic-Persian Gulf to the north of the Caspian Sea, which should be there. And taking into account the problem of climate change, we can say that the general equation is this one. In the world, we should divide by 2 our CO2 emission before 2050, and at the same time, we should be able to double our energy production for the big needs of the emerging countries, the major economies outside of OECD. And this is very difficult because today 80% or slightly more of our energy production is burning oil, burning coal, burning gas, and presently sending everything into the atmosphere. So it is quite a revolution to achieve. But in addition, when we say halving, dividing by 2 the CO2 emission of the world, taking into account that it will increase in China, India, Brazil, etc., means that in the OECD country, we have to realize a factor 4 of reduction. This is very ambitious. By the way, it is the official target of the European Union, but it is very ambitious, and the present target which have been decided or at least indicated after Copenhagen fall short of this target. So this has been already shown a number of times. It's very important. In order to go from the reference scenario of the IAEA to the 450 scenario, more than half of the efforts will have to be on efficiency. Efficiency in end use, efficiency in power plants. Then we will have to increase a lot the renewables as compared to their previous increase in the reference scenario, and also increase nuclear, and implement, and from the previous talk you see it will not be easy, implement at a large scale carbon capture and storage. Now, you see that renewables and nuclear share the same quality of being low carbon energy sources. On this diagram, you can see the amount of CO2 or equivalent CO2, all greenhouse effect gases included, when you produce 1 kilowatt hour of electricity. It is the same electricity at the end, so it's easy to compare. And if you do it by burning coal or lignite, you see it's roughly 1 kilogram. If you do it in a modern high efficiency combined cycle gas turbine, it's like 500 grams. If you are able to implement carbon capture and storage, you can probably go down to 250 grams per kilowatt hour. Now, if you take any kind of renewables or nuclear, you're in a ballpark which goes from, let's say, 10 to 30 grams. So that's the main advantage of both nuclear and renewables. And I say both because I'm completely convinced that they are the same package, really. They are not really competitors. They are in the same package. And Areva, for instance, which is a kind of a leader in the terms of nuclear development, is also more and more trying to be a very important actor in renewables by selecting offshore wind, electricity from biomass, and concentrated solar. So we are not in photovoltaics. It's not our kind of beauty, if you want. But we are really, really deep in renewables because for us, nuclear and renewables are just part of the same package. This has already been mentioned by saying that in China there is a new coal plant started every 10 days. And you can see that it has already started. If you look at this coal production from 71 to 2001, it was reasonable, smooth growth, if you want. But you see a very, very drastic change of slope from 2000 to 2007. And if we focus on China again, the Chinese production of coal was 1 billion ton in 2000. But it was 2 billion in 2005 and 3 billions in 2008. Now that's a real concern, really, because as you know, and as you remember from the previous slides, coal is not the cleanest fuel possible. Now what is Renaissance, really? Well, in terms of nuclear power, you have on this map, in green, all the countries which in 2008 had at least one nuclear plant producing electricity. So I told you it's only 30 countries, but it includes some giants like China, India. So in fact, it's more than half of the world population. But in terms of countries, it's a very limited number. And what you have in yellow are the countries which, during the same year, 2008, went next door to the International Atomic Energy Agency in Vienna to ask officially some help from them to consider whether nuclear should be part of their future mix. So they are not countries actually starting building plants, but they are countries which now are officially considering going nuclear. And if I had shown the same picture, not referring to the year 2008, but to the year 2005, for instance, which is not so far away, green would have been identical. Not one more, not one less countries have actually made nuclear power. But at the time, the number of yellow countries would have been very different. You would have had Turkey, Iran, North Korea, Vietnam, and that's it. So the Renaissance is there somehow. The taboo somehow has been lifted. More and more countries are considering going nuclear. Will they go all the way? The question is still open. But also in terms of construction, you see that in 2008, at the end of 2008, there were 44 plants, nuclear plants under construction in the world. Well, 2 years later, it's 54. So there again, there is somehow a beginning of Renaissance. If we turn now to the IAEA forecasts, you have on this slide in pink the actual number of billions of kilowatt-hour produced country by country in the year 2008. And then green plus yellow, you have the low or high forecast for 2030. The main difference between the low and high forecast is, in fact, in the actual operating life of the existing plant more than new plants. Because one of the characteristics of nuclear power, it takes a long time. If a country, one of the yellow countries of the previous slide, decided today, okay, we will go nuclear, they will not have the first nuclear kilowatt hour before 2025 at the earliest. So it would not have such a big impact on the assumption for 2030. The characteristic times are very long because you need to establish a full infrastructure, both technical, administrative, regulatory. Then you need to find suitable sites. You need to build the plants. All this takes time. And you need to train people, train people, train people. But now if you look at this forecast for whatever they want, you see it's going to grow in North America, in Latin America, in Eastern Europe, in Africa, Middle East, is going to grow anyway very, very, very much in the Far East. But you see that the projections for Western Europe are kind of difficult to decipher. It might grow significantly, but it might also start collapsing somehow. Well, those were the projections made in 2009. But if you look more closely to Western Europe, the picture in the very, very recent years has been improving, I'd say, improving the way I see it. So we came from Atomkraft nahe Danke to Atomkraft vielleicht. Nuclear, perhaps. Not yet, ja bitte. But we are on the way. So if we look now country by country somehow, you know that Finland and France are building 2 big EPRs. The one you saw on the the first picture of my presentation was Olkiluoto in Finland. Romania and Bulgaria are starting to build a Russian Romania is building other old Canadian type reactor, and Bulgaria is starting now to build a Russian type reactor. One thing which is very important, when the European Union came from 15 members to 25 and then 27, the mood has changed. And the mood has changed notably in the European Parliament. And it is very important because when we were only 15 member states within the European Union, the majority was rather strongly anti-nuclear, led by this very country, Austria. But at the time it was not so important because the European Parliament had no power. But since the European Parliament got rid of the Center Commission, then it acquired a lot of power. Unfortunately, it acquired also new members which are much more balanced about nuclear power. So there is a big change of mind. If we take now the case of the UK, United Kingdom, it is also very interesting because in 2003, which is not so far away, the official policy expressed in a white paper was we will decrease by 65% our CO2 emission in 2050 just by developing renewables. And we will not hasten the end of life of nuclear power, but will simply not renew them. And then in 2004, something happened, just a year after. Well, UK realized it had become importer of gas. And that was a big change, because until 2004, the UK was the European Emirates. They were the only country within the European Union which was actually net exporter of energy. Becoming importer of gas at the time when the gas price on the internal market was, in addition, multiplied by a factor 3, they just put the old 2003 report to the dustbin and developed a new policy, which is now, well, we will at least replace the dying plants by new plants, I mean nuclear plants, as long as the government doesn't have to put a penny in the pocket, which is fine. Then, very significant also, Sweden in 1980 had passed a law following a referendum saying they would shut down all their nuclear plants by 2010, this very year. Well, last year they said it was not very reasonable, so not only will they keep their 10 operating plants, but they plan firmly to replace them when they die out of old age. Italy is the only country in the world where an actual operating nuclear program was shut down brutally by the government in 1987. And now they are simply reversing this position, saying both in terms of CO2 emission but also security of supply, they had to go back to nuclear. And okay, I will switch just to say, even in Western Europe, there is indeed the pendulum is slightly swinging back. And this was possible, or did trigger, it's very difficult, it's more or less a chicken and egg problem. But the public opinions also have changed over those last few years. And then you have a comparison of two so-called Eurobarometers. A Eurobarometer is not a very short telephonic poll with 900 representative people. It's a face-to-face interview with 1,000 people from each of the member states. So 25,000 or 27,000 people were interviewed. No modification taking into account the population of the country. So somehow Cyprus has the same weight as Germany in this poll. But you see that in winter 2007, at the question, are you more or less in favor, more or less against nuclear power, the more or less in favor were 37%. 3 years later, 44. And at the same time, the against came down from 55 to 45. So there is, even in terms of public acceptance, a real shift of opinion, which comes from all what has already been explained by the previous speaker. Concern about climate change, uncertainty about security of supply, concern about the rising cost of energy, all this somehow, and the fact that in the meantime there was no nuclear accident, all this has played in favor of changing somehow the public mood, even in Europe. But as I told you, there are issues about it. First, to actually materialize this renaissance, we have to fill at least two conditions. One, keeping economic competitiveness with the best competitor fossil fuel. According to the countries, it would be with gas or with coal. Second would be public acceptance. In democratic countries, nuclear will not be built if there is no public acceptance, full stop. And there are some additional condition for this public acceptance. No severe accident. As you know, there has been one severe accident in this story of nuclear plant, and 24 years after we are still speaking about it. Second, accepted way of disposing of the long-lived radioactive nuclear waste. And third, which is a little more subtle, I'd say no rampant proliferation of nuclear armaments. As I will explain, this is more subtle. Now, if all those conditions are actually filled, we will have a renaissance. Instead of having 400 reactors operating in the world, we may go to 2,000. And a question which is presently moot, which is, will there be enough uranium resources? With the present fleet, it's not a problem. But if we come from 400 reactors to 2,000, then the question will arise, and the answer will be we will have to change the present technology. Still within fission, we will have to change from the present slow neutrons reactors, if you want, to the fast breeders, and then the question of resources will be pushed a few millennia away, which is fine. In terms of competitiveness, we are lucky because only last month was issued the 5-year study on the evaluation of future costs of producing baseload electricity. It was a study which was carried out jointly by the International Energy Agency from Mr. Houssin and the Nuclear Energy Agency, which is a sister organization within the OECD. And their results, you see, depends on the region of the world and also a lot about the discount rate which is taken as an assumption. Why is it so? Because in nuclear power, it's exactly like in renewables. You have a big investment and a small operational cost. So the weight of the investment part depends a lot on the cost of money, or if you prefer, on the discount rate. So by taking the 5% discount rate, you see that in all countries, nuclear is supposed to be competitive. Now, the hypothesis is for a plant to be ordered now, to enter into operation in 2015, let's say, and then to operate for the next 60 years. And when I say that, you understand that the assumptions about fuel cost, gas or coal, from 2015 to 2075, well, you can make any assumption you want somehow. So this was a kind of expert's vision. Maybe wrong, but maybe right. And you see that in all cases, at present, nuclear power appears attractive. Now, if I had taken a discount rate of 10%, nuclear would have been less attractive, but still in the broad range of projected competitiveness, and certainly still in Asia. So I have also to emphasize that all costs are taken into account. When I have discussions, especially if there are people from Greenpeace around or so, they first say, well, but it's because you don't take into account all the costs. No, in those kind of studies, all costs are accounted for, and even the cost of CO2 for the competitors. As you can see, there is a $30 per ton of CO2 taken into account to make the comparison with coal and gas. Now, 30 is not big, but it's more than the present cost on the of the exchange rate in Europe. 50 is probably more reasonable in the long run. But there again, I may be wrong. But what the important point is, what is taken into account are provision for dismantling, handling and disposing of the waste, and R&D costs are also included in all those. Now you can say, okay, but uranium prices. Well, uranium price is no more stable than oil price or gas price, but its impact on the total cost of kilowatt hour is much smaller, because today, when you produce 1 kilowatt hour from a nuclear plant, most of the costs come from concrete, steel, and brains. And uranium accounts for less than 5%. So when uranium prices is multiplied by 3, which happened in the past, and even more than that, well, it's only plus 15% of the total kilowatt hour cost. When the gas prices is multiplied by 3, and this happened too, then the cost of electricity from gas turbine is multiplied by 2. That's a big difference. Second point, no more severe accident. And as you can see, this is a picture of Chernobyl. Chernobyl has changed the very safety philosophy of the reactor designers and of the safety authority which controls us. Before Chernobyl, the basic of the design was make the maximum accident. And by maximum, I really mean accident, the full meltdown of all the core of the reactor. Make it such a low probability that somehow, by multiplying the probability by the consequences, it would remain, quote unquote, acceptable. Well, after Chernobyl, no longer. So now we still are trying to target a very, very low probability of an accident which would destroy a plant and cost a very big amount of money. But we have to demonstrate that if this accident was actually to happen, it will not lead to a massive contamination of the environment. This is no longer allowed on any conditions. And these new designs of plants, the so-called generation 3 plants, take into account this additional condition, still keep the probability of accident very low, but demonstrate that if it were to happen, most of the radioactivity, almost all of the radioactivity, but I say almost, would remain contained within the reactor building. That means that the reactor building itself should be strong enough or protected enough to remain intact even against the aggression of the accident itself, which is not negligible. So if you take the presentation of the EPR, the one which we are building in Finland and France presently, and 2 in China, by the way, you see it has first a lot of devices to reduce the probability of the accident. For instance, we have 4 completely redundant train of safeguards. One is enough to put the reactor back into safe position after the beginning of an accident. There are 4 of them. And to make sure that there is no common mode between the 4, they are completely separated also geographically. They are located, each of them, in separate building with no common mode, which is very important. If the core was going to melt down, it would become a kind of volcano lava, which is called corium. Well, it will flow in this region where there is a core catcher, where it would be spread, and then passively, by passively I mean without operation from the operators. It would be passively flooded by a big water tank which is just around waiting for it somehow. And then you have a number of additional features to protect the containment against any risk of hydrogen explosion, water explosion, etc., etc. And this is a better picture when you can see here the core catcher, the tank, and then actually on the spot, if you want, and those workers give you the scale of the construction, you have the pit where the reactor pressure vessel will sit, and then a channel leading to this spreading area. And all around you can see the vast size of the huge in-reactor water tank, which will be used to solidify and cool on the long term the solidified corium. Once solid, it won't move. Now, there is not only Chernobyl to take into account, but after 9/11, you know, I would say on 9/12, all the safety authorities in the world rushed to their favorite operator to say, well, what would have happened if those planes, instead of rushing into the World Trade Center, had crashed into your plant? What would have happened? And of course, the answer is, we don't know. That was not part of our original scenario. So we spent a few years working to see what would have happened. And in France, the safety authority said officially that even on the existing plant, if such a voluntary crash had happened, well, the plant would have been extremely damaged, but that would not result in massive contamination of the environment. But in the new plants, EPR, the answer is much more positive. It is, well, the plant will resist a plant aggression, and whatever somehow the elevation or the angle, and whether it is a big, large commercial jet, but which will have to be rather slow not to miss a small target for it, or a fast, much lighter, but a very fast plane, military plane, which can in fact actually target the plant. In both cases, we were able to convince the safety authority in France and Finland, and we are in the process of completing the demonstration with the US NRC, that indeed this plant is very sturdy. You have seen the thickness of the concrete on the pictures to give it. It's really big. Now the last, the second best last condition is acceptance of the disposal of long-lived waste. And as you can see on this was a secondary question of the previous Eurobarometer, which was asked only to those people which were slightly against or completely against nuclear power. And the question was, well, if you were convinced that we could dispose safely of the radioactive waste, would you change your mind? And as you can see, a non-negligible proportion, like 39% of the people polled, answered yes. If that were the case, we would become more or less for, not drastically for, of course. So I have first a few words to add. First, what is radioactive waste? Well, it's not so easy. Most people are very afraid of radioactive waste, but have not the slightest idea what it is. Is it gaseous, liquid, solid? Which form? Well, the long-lived radioactive waste all come from the nuclear power. Short-lived come from a lot of other places, labs, hospitals, etc. But the long-lived radioactive waste come from producing power, from making fission, from having fission products after you have produced your energy. And whether they are waste or not depends on what do you intend to do with them. That's not specific to nuclear. I mean, you spoke about plastic bottles. If you throw your empty plastic bottles in a standard bin, it is a waste. If you put it in a specific container for recycling, it is just a new raw material somehow. Recycling makes the difference. Well, in nuclear power, it's the same. When one fuel element, like you have on this picture, has stayed 4, 5 years in a nuclear core producing power, it's no longer in a position, it's no longer able to produce power. So you can say, okay, this is my waste. 2 countries have actually made definitely this choice. It's Sweden and Finland. And so they have developed a process by which they dispose of the spent fuel as the final waste. Now, other countries, for instance, France and Japan, say, well, in this spent fuel, you have indeed a big amount of final waste, meaning that you don't have any use for them or planned use, but you have also remaining a lot of materials. You have uranium and plutonium, which are quite able to be recycled to make new fuel. And so we decide we make the separation, we recycle what's recyclable, and we condition what we consider as a final waste. And so we have a process which is slightly different, which goes to a reprocessing step, and then, of course, goes to final waste disposal. And I would say that most of the other countries are sitting in between, having taken no decision and say, okay, we will just make interim storage of the spent fuel, and someday in the future we will decide. So you see, you have kind of 3 strategies, or I would say 2 strategies and a non-strategy in between. So a few words about waste. We usually determine 3 categories of waste, mostly. First, waste which are of low activity and do not contain significant amount of long-lived waste. Now, you are all teachers. Something which is very important and very counterintuitive is the longest the lifetime of radioactive nuclide, the less dangerous it is. It is usually felt quite the reverse. Sometimes people say, look, iodine-129 has a half-life of 15 million years, which is true, by the way. Well, that means it decays very slowly, so it emits very little radiation. So you could put all the iodine-129 in your thyroid, you would have to wait a few centuries before your first cancer. And you are likely to be dead before, from other things, I mean. So if you look at nuclide by nuclide, if it's very short-lived, just wait, it will disappear. It is very long-lived, no problem. It is those which are in between, which are the actual problem. But don't forget that long-lived doesn't mean dangerous, not by itself. Okay, so then you have the A waste, which have no isotopes whose half-life would be bigger than 31 years. Then you have those which have long-lived half-life, but which have no big activity. And then you have those which are both. It's a package where you have both short-lived, very active fission products and a number of long-lived higher actinides, which after 1,000 years will only appear then, but will stay a long time. So those to give you, now just the question of amount of waste. If I take a country like France, where, as you know, 75 to 78% of the electricity comes from nuclear power, so it's probably one of the biggest amount of nuclear electricity per capita. The total amount of toxic waste generated per Frenchman in an average year is of the order of 10 kilograms. Those are actual toxic waste, which can only go to 2 licensed disposal sites, and which will remain toxic more or less eternally, because most of them are like arsenic or heavy metals. So just, okay. This is a good standard to compare it. The total amount of radioactive waste per Frenchman is of the order of 1 kilogram, out of which only 100 grams have actually long-lived isotopes in them. And out of which only 10 grams are those high activity, high level waste, where you have both very active but shorter lived isotopes and long lived isotopes, which will appear later on, which will appear later on, sorry. So it's not a question of quantity, you see. It is very dangerous, but there are quantity which we can manage. And in fact, we do manage them. So they are not orphaned. They are not spread out in the environment. They are concentrated under surveillance. They have the proper conditioning to make them resistant to corrosion, which would be probably the only processes by which it could spread again. And presently, they are interim stored in the reprocessing plant when you have 3 kind of gymnasium. I would say probably 3 times the size of this room, not huge, you see. And under this guy, you have 15 years of the vitrified high-level waste of all the French nuclear plants for 15 years. So you see, it's not a problem of volume. But this is only interim storage. This is not a final solution. And we had, since June 2006, a law giving the roadmap of the final solution, which says that first, the proper way of dealing with spent fuel is recycling what's recyclable and only dealing with the final waste. Those would be interim stored for a given time and then would go to deep geological storage, which has to be reversible. Just because if we find something better later on, we don't want to be unable to put it into operation. So we are not planning to take back the packages, but we are making sure that it could be done if in the future there was a better mousetrap, if you want. This site has to be opened before 2025, so we are just in the process of making all the preliminary qualification of the geological stratum, which has been already selected, which is the Calavo-Oxfordian argillite, which is under the whole Parisian basin. So we are not lacking clay, sorry. But we have not selected the precise way where it will be. This will have to be mostly a matter of local acceptance. And then, at the end, the waste producers pay for everything. So it's just the people buying the electricity which pay for the waste. It's not through the taxes. It's about the same people most of the time. But okay, philosophically speaking, it's probably better this way. And I would say France has still a policy of not disposing of foreign origin nuclear waste in France. So we are allowed to make reprocessing services, but then the final waste goes back to its original owner. So just to show you what is an actual disposal site of low-level, short-lived waste, this is licensed under control from the safety authority and has a capacity of roughly 1 century above. This is the underground lab, the one which has been dug 500 meters below ground in the clay formation I've just mentioned, which incidentally has been stable for 150 million years, so it's good clay. And there, a lot of experiments are carried out, not only to qualify the initial quality of the clay, but also how those quality would be altered by digging galleries, putting hot packages in it, and making all the proper measurements. Very interesting lab to visit, by the way, for geoscience people. And before leaving the long-lived waste, I just say a few words about Oklo, because just a show of hands, how many of you know about the Oklo? Okay, you are once again.
I know from Bertrand.
Okay, but a short speech. You know, no, but it's fascinating. This is a uranium mine in Gabon, Oklo being not too far from Franceville. And in 1972, we have discovered that in this specific uranium mine, not one, but 17 different nuclear reactors have been operating. They have been operating 1,960,000,000 years ago. And this one, which has been kept, as a museum, has been operating for 800,000 years before shutdown. Now, we are discussing whether our plants should stay in operation 40 years, 60 years maybe. Okay, 800,000 years, but it was a small power. Okay. The point is that for almost 2 billion years, all the long-lived products of the fission which was produced during 800,000 years have been contained within a few inches from the place where they were produced. And this is absolutely fascinating because it shows that the idea of using geological storage is far from stupid. It has worked. You know, we need to make sure we can contain the radioactive products package that will go down for 100,000 years, maybe 200,000 years as a maximum, which is huge as compared to human history, but which is peanuts in terms of geology, and certainly very far away from 2 billion years. Now I come to the last point, which I told you is a little subtle, which is about, does nuclear power development increase the risk of nuclear armaments development? And I say increase, because in any case, the risk is not zero. You just have to look at history. All the countries which are presently called nuclear weapon states, USA, Russia, which used to be Soviet Union, UK, France, and China, have had bombs before kilowatt hours. It's a sorry state, but it's easier to make bombs than plants. So we can perfectly develop nuclear weapons without nuclear power. And if I take the case of Israel, for instance, which everybody knows has what's enough to make 200 bombs, it doesn't have a nuclear plant, nuclear power plant. So the question is, the risk exists whether or not you have nuclear power. The question is, does developing nuclear power increase or decrease that risk? And that's where it becomes subtle, because you have factors going both ways. On the one hand, when you train people, if they're able to calculate a plant, they're able to calculate a bomb. No, calculating a bomb is not making it. But okay, you are somehow making proliferation of brains. Accepted, okay. If you develop nuclear power, you will have on your territory big amounts of fissile material. They are not the same that you would need to make bombs, but there could be a shortcut if you took the political decision to make bombs. So those are on the negative side. But on the positive side, if you develop nuclear power, you will want to make it within the international community. In fact, you will need help from the international. And then one of the first prerequisites will be signing and ratifying the Non-Proliferation Treaty, accepting the safeguards, control, and inspection of the International Agency in Vienna here. And those inspections are efficient. If we have presently crisis in North Korea and in Iran, it's because we have seen things which were not supposed to exist. But at the very end, it is a question of politics. But you see, there are things going both ways, and so it's difficult to make its mind completely. But you can ask the question in reverse. Would stopping down nuclear power erase the risk of nuclear weapons? The question is, of course not, but it's even the reverse. Because since we have entered the discussion to reduce the strategic armament, the SALT, and then START negotiation, a big amount of nuclear weapons have been actually dismantled. But the fissile material are still here. It would not be a big problem of remaking bombs with this fissile material unless you make fuel out of it and burn it in plants. And so it is presently what is happening. We in France have been somehow transferring the technology of plutonium fuel to the United States in order to be able to burn the excess weapon-grade plutonium of the United States in reactors, presently reactors from the Duke power, but the TVA is on the line as well. So if everything is nice, if we have a big renaissance, what can be expected this amount of renaissance? Well, we give you our forecast, which you can see is kind of mid-range among a number of international forecasts. And we take from the previous 374 gigawatts, which were installed in 2007. We take the number of gigawatts which at present are supposed to be retired from service, but we correct them with the plant life extension program. Now that's something which is not completely known, but for instance, in the United States you have presently 104 operating nuclear power plants. They were all licensed at their start for 40 years. But out of these 103, already 58 have received an extension of 20 years. So coming from 40 to 60 years. And so when we make our own assumption of this trend, we say, well, okay, probably the amount of plants to be built from now to 2030 is almost of the same order of magnitude like the present fleet. So this is a huge challenge for us. We'll have to train people to increase the fabrication facility. Most of them have been put out of service during the 2 decades of slump somehow. And the question is not so much how strong is the competition between the vendors, but whether all the vendors together will be able to supply this kind of market. So we have to go back to the past, if you want. In the past, it was in 1979 that there was the maximum number of reactors under construction at the same time. And that was above 200. We went down to 20. Now, I told you 54. So we have started going up the slope again. Now, okay, if everything is well, will there be enough uranium for everybody? Well, every second year, there is the so-called Red Book, which is published jointly by the IAEA and the NEA, the sister organization of Mr. Houssin, which tries to establish what's known about uranium reserves in the world. And as you can see, are considered as identified reserve 5.5 million tons of uranium, out of which undiscovered but firmly believed to exist, I would say, you go up to 15 million tons. This is only in conventional uranium, because like oil and gas, you have also unconventional uranium. For instance, all phosphates in the world have a high content of uranium, and the uranium content of the phosphates is bigger than the content in the traditional uranium ore as such, but at a price which is difficult to articulate really. So what does that mean? We say 15 million tons. The present consumption rate is of the order of 70,000 tons per year. So that's what I told you. With the present fleet, if we simply renew plants by plant, we don't have problem for 2 centuries, because of course all those estimations are slightly below the reality. If we increase the accepted cost of extraction, we will increase the resources, and we will make also some additional technology progress in the extraction process, which will also increase those figures. But just to say, with the present fleet, it's not an issue. But if we come from 400 plants to 2,000, it becomes an issue. And then the answer will be, well, but we know already that if we change the technology of the reactor itself, which means changing the physics, in fact. In the present-day reactors, for instance, after a fission, we slow down the neutron very quickly before it undergoes the next fission. It goes from 20,000 kilometers per second to 2 kilometers per second. So you see, it's very different range, very different physics. If we keep the neutron fast from one fission to the other, then we change completely the amount of energy we are able to extract from the same given amount of uranium. And we change it by 2 orders of magnitude in round figures. So instead of speaking of century, we are down in the millennia, which is sufficient. So we present this in terms of reactor generation. Those, the pioneers' facilities, were, let's say, just a big series of prototypes, one after the other, different, no standardization, no series effect. Presently, most of them are decommissioned. Those, which we call generation 2, are those reactors in the world which are producing 15% of the world electricity. And when we are decommissioning the first, operating the second, we are starting to build generation 3, so the EPR and its competitors, which are somehow the same, plus the post-Chernobyl condition of no severe accident, at least no severe outside. And when we are starting to build those, we are in an international scale making all the development for the next generation to be commercially available somewhere around 2040, 2050 maybe. But we don't know when we need it. That's the problem. Because you see, it will depend on the strength of the renaissance. If we only multiply by 2 the present fleet, we don't need generation 4 by 2040. Are agreeing on the R&D to be carried out for those plants to be commercially available by, let's say, 2040. With advances in sustainability, that's mostly resource utilization, factor 100 floating somewhere, long-lived waste disposal. We can fission heavy nuclei like neptunium and americium in those plants, not in today's plants. So we may want to do that. Not sure, but we may. And then better physical protection and still keeping the economics competitive, because as you see, each time we make more modern plants, they tend to be slightly more expensive. Sorry. Competitive in various markets and opening the range of application of nuclear power, not only electricity as of today. Today there are also a few submarines, but it's not very negligible. But we think that water desalination is a very short-term application and very needed. I mean, if most of the Middle East countries are now considering nuclear, it's maybe more for fresh water than for electricity as such, even if electricity is used to make fresh water by reverse osmosis, really. So it's very important. This is short-term. Longer-term, process heat for industrial application, hydrogen production, to make syn fuel with biomass, for instance, those kind of things. Most of the fuel you make from biomass today are lacking in hydrogen atoms. So the idea of having a kind of symbiosis between nuclear and biomass is strong in our mind. So those are 6 kind of potential design, out of which a few are meant to be commercially deployable by 2040. Not all countries part of the Generation Forum are interested in all of them. For instance, in France, we are really deeply interested in the sodium-cooled fast breeder. We look forward to the possible, later on, gas-cooled fast breeder, and we keep an eye on the high-temperature reactor. We are not interested in the others. And each country somehow makes its shopping around within those 6. And then spend the R&D money, which is big, because before having something commercially deployable, you need first to have, I would say, a demonstration, then a prototype, then a commercial plant. Takes time. So this is the end of my talk. If you are very wealthy, you can buy this book, which is written also with an oil man. It's a double. But you can also, for free, visit my site, which is partly in English. Thank you.